Let's actually zoom in how the velocity field would behave. So let's look at on the upper side of the airfoil first. We have constant pressure lines. So let's say, to make it easier to analyze, let's just think about these lines as cliffs, okay, over which the pressure suddenly jumps. So let's say this is P infinity, okay, this is P infinity plus a certain delta P. So that's a pressure increase. And let's assume the pressure has decreased over here. That's P infinity minus a certain delta P prime, right? And we know after the airfoil, we have to go back to P infinity. So let's just assume the pressure jumps and falls and then, jumps up again, right? And see how the velocity field would change. We know the velocity upstream is horizontal and U infinity. All right. The question is, how would it respond to a sudden jump, albeit very small jump in pressure? Think about what we studied about oblique shocks. How would the velocity change? Yes?
I expected it to go slower because the push is increasing.
Yes, it has to go slower because the pressure increases, right? So over here, just to think about if you're inside a shock when the pressure is increasing very rapidly, what is the pressure gradient as a vector? Or what is the force resulting from the pressure gradient? Which direction does the force point towards? Yeah, right, orthogonal to the pressure contours, right? The gradient is always orthogonal to the contour, right? That's another vector calculus fact. So the force is pointing towards this direction. That's the force, the pressure force. All right. So how would the velocity as a vector respond to the force? Yeah, it has to go upward a little bit, right? So if you expand the velocity into two components, one component is tangential to the shock or tangential to the pressure contour, that velocity gradient would not change at all. But the other component, the component orthogonal to the shock, would be reduced, right? It's as if it's going, if we slide along the shock according to this tangential velocity, it's encountering a normal shock. Right, the velocity is going to be decreased. So as a result, the tangential velocity stays, the normal velocity decreased. We get a velocity that's turned upwards and slowed down by a little bit. And slowed down. Yeah. Okay. Now, when it encounters the next wave, so this is a shock. This is a shock as the pressure is increased. This is an expansion because the pressure decreases, right? How would velocity respond to an expansion wave? It'll speed up, right? Exactly the opposite effect. But again, the velocity component along the expansion wave would not change. Only the normal direction velocity would speed up. So how does it respond to a turning of the flow? It'll turn downward, right? It'll go that way. Okay? And now if you work out the math, after it encounters, this is another shock wave, right? This is another shock wave. It is going to go exactly horizontal. So basically the amount of turning at the limit of a small delta P is actually exactly proportional to the delta in pressure. So as you go back to the same pressure, you get back to a horizontal velocity, right? This is another shock. It turns upward by a shock. Okay? Does this look like actually the shape of the upper side of an airfoil? It does, right? So that's exactly how the pressure has to behave, because on the upper side of the airfoil, the flow has to follow the slope of the airfoil. right? The velocity has to follow the slope, and the slope is actually exactly corresponding to an increase or decrease of the pressure. So the pressure actually responds to the slope of the airfoil. Okay, if the airfoil on the upper side is sloped upwards, the pressure is proportionally increased according to the slope. If the slope is downward, the pressure is proportionally decreased from the free stream. Right? That's why I'm saying designing a supersonic airfoil in some sense is easier, right? I mean, designing a supersonic airfoil that doesn't have to fly at supersonic regimes, which is never the case, is easy because the pressure actually responds to the slope rather than responding to the curvature. I mean, the thing that makes it hard is that a supersonic airfoil has to actually fly through subsonic speed and the transonic speed and then supersonic speed, right? That's the hard part. The supersonic part is the easy part. All right.